Alright folks, Chapter 10 is just an extension of the work we did in Chapter 9 with sampling distributions. We've got point estimators that go along with our sample statistics. Okay, those are sample statistics that estimate the population parameters. So p hat was our sample proportion. If we don't have our population proportion, then we use that to estimate it. They're used interchangeably. Same thing with x bar, that's our sample mean, and it's used to estimate the population mean. When we don't have it, that's mu. And then finally here, S, our sample standard deviation, estimates sigma, our population standard deviation, when we're not given that information or those parameters. So with our work from last chapter, we had talked about sampling distributions being normal under given conditions. So today's focus is going to be on means. So we had the sampling distribution of sample means, and when we had that normal distribution, it ended up that the mean of the sample means was actually the population mean. Okay? So because of symmetry, that ends up saying for us that our mu, we can be, because of our Excel formulas and the empirical rule, we can be pretty sure that a certain percentage of these intervals that we're constructing will actually have that population mean in it. The idea of this being a confidence interval. Okay, so we'll get into that a little bit more detailed after we just kind of make sure we understand some symbols and some notations as far as it goes with these estimators. So that's what our first three examples look like and what some of your questions on your homework are going to relate to. It says the mean monthly water bill for 140 residents of the local apartment complex is $74. So when we're reading through a problem, we're going to look for either this is a sample measurement, a statistic, or this is a population measurement, a parameter. And then, of course, what it's actually measuring, a mean, a proportion, a standard deviation, something like that. So this one, it tells us mean, and because of its being for just 140 residents, it's the sample mean. So our sample mean is denoted with x bar, that's our symbol, and they tell us that is $74. Then it says, what is the best point estimate for the mean monthly water bill for all residents? So the point estimate is always the sample statistic used to predict what the population parameter would be. So it gave us the sample mean. That is the point estimate for the population mean, which is what they wanted. So that is it for these ones. They're not always going to be perfectly given to you. So on the next one it says, what is the best point estimate for the population standard deviation if the sample variance? So they gave us that we want to get the estimate for standard deviation, but they're giving us variance instead. So sample variance was given. And for that, sample standard deviation is S. And remember, the relationship between standard deviation and variance is just standard deviation squared. So our symbol is S squared. They gave us that as 46.8. Didn't give us a label on this problem. So from that, we can find the sample standard deviation, which is just regular S, by taking the square root of that. And that is our point estimate because that is our sample statistic that estimates the parameter that we're focused on. It says round your answer to 1 decimal if necessary, so we're just going to tuck away those extra digits. No labels for this one. It says consider a sample of oil filters. Their diameters are measured and found to have a variance of 2.04. Give a point estimate for the population variance in diameter of oil filters. So this one's exactly the same as the last one. It gave you from a sample the variance. So it wasn't in the same sentence, so you have to read a little bit between the lines, but that is a sample variance of 2.04 for this one. And then from that, we're going to find the sample standard deviation just by taking the square root. Doesn't tell us to round on this one, so that is our final answer. Okay, these are estimators. In a perfect world, they would be exactly equal to the population parameter that they relate to. However, that doesn't happen perfectly in real life. So what we're going to do is talk about how we decide whether an estimator is reasonable or good. And that's what we're going to talk about in terms of interval estimators. So we've done a lot of problems where we want to see if the actual mean differs by some number from the sample mean, or differs by some number from the sample proportion. That has been building us up to the idea of a confidence interval. So, recap for today, we're just going to focus on means. So that applies with our central limit theorem. We only have the normal distribution, the bell curve, if one of two things is happening. One, we are told that the sample size is reasonably large and is bigger than 30, or we are literally told that this is a normal distribution. So we have to have that happen. Otherwise, we cannot use our Excel functions with norm.dist or norm.inverse because we don't have a normal bell-shaped curve. Okay, so those things are the basics. But with our sampling distribution, the standard deviation of the sample mean has this formula. What we're going to talk about is that differs by amount that we were referring to is the distance one way or the other. That's going to be called for us the margin of error. Okay, so I want you to just sketch a little picture of this. We're going to have our sample mean in the middle, and then each direction we're going to go a margin of error. And that margin of error is going to be determined by what proportion or what percent confidence level we want to be. So remember, on your bell curve, you don't have to draw this, just kind of listen here. On your bell curve, one standard deviation each way is 68% of all values will fall within one standard deviation. And then within two standard deviations, that was 95% of all values, okay, would be within two standard deviations. And then almost all of the area under the curve is captured with 3 standard deviations away. So this is my standard deviation of the sample means when I talk about sampling distributions. So we're not going to necessarily be given 1 nice value, 2 nice values, or 3 nice values to just do this. Instead, we're going to kind of work backwards. You're going to be given, what if we want to be 96% positive that our true mean falls within some interval? Well, that's going to mean we have to calculate what value of standard deviations away we are, and that for us, remember, is a z-score. Okay, a z-score is the number of standard deviations away. So our actual formula for margin of error isn't just this standard deviation, because it's not always nice. It's the z-score, however many away, times that standard deviation to give us back into those raw intervals, because it's not always a nice 1, 2, 3. Okay, and then we can add and subtract from the mean that differs by, go above and go below to construct the interval low value, high value that our actual proportion, hopefully falls in between, or our actual mean, excuse me. Okay, it works the same with proportions, but we're focusing on means today. So we're going to have 2 different formulas today, and I've been talking about z-scores because that's what we know right now, and that's what we've been doing. So we're going to start with the confidence interval for when it's a z-score, and then we'll come back to talk about if we don't know some of the information and where this t is kind of coming from. So this very first thing we're going to do is make sure that all of our situations are normally distributed, or we have n greater than 30. Okay, those mean the same thing, means we can use Excel formulas to do our math. Okay. Second thing we're going to look for, and we're going to focus on the yes first, is the population standard deviation known? Because if so, that's how it correlates to a normal distribution with this formula and using z-scores. So this first example, it says, suppose a simple random sample of size 100 has been drawn from a population. Okay, size 100 tells us two things. That is the n value, 100, and that because it's larger than 30, we have a normal distribution. Then it says we have a standard deviation of 200 and a sample mean of 150. Okay, so we've got this 200 and we've got 150, and we want to be careful with our symbols so we know exactly what they relate to in terms of this formula. So it said the random sample 100 has been drawn from a population with this standard deviation, which means this standard deviation is the population standard deviation. And we're going to practice using what we see on our formula sheet. That is the Greek symbol sigma. It's lowercase. And I'll just extend this out so we can see that whole thing. So then the next one, it says, was our sample mean. That's our x bar, 150. Find and interpret 95% confidence interval. So here's what it's asking us to do. And we'll sketch it on this first one. You don't have to sketch it after that. We want to construct an interval around our mean so that the area under the curve here is equal to 95%. So in order to do that, we have to know what is going on here, because when we do our norm dot inverse values, okay, we know that it's area to the left, not area in between two values. That's our standard. Okay, so we have some things that we need to find in order for this to work, but it's all based on that 95%. So the first thing I'm going to have you write down is just that confidence level, CL for that, is 0.95. If I care about what's going on over here, then that's going to be the leftover percentage. So 95 to 100 is 5%. That's alpha. Alpha in statistics relates to what's called the significance level. But for right now, I'm just going to refer to it as leftovers. Okay, so alpha over 2 is leftovers. 0.05 were the leftovers, and I'm splitting it in half because there's 5% between these two tails, but I only want one of them. Okay, so that's where this subscript alpha over 2 is coming from. It's just getting that left tail for us for the left side of the interval. So if that is my percent or my proportion over here, I can find the correct z-score, the z alpha over 2, by just using one of my Excel functions. As a reminder, all of the z functions go with .s, and when we're trying to find the score, not the probability, it's the inverse. So it's norm.s.inverse, and you just grab that alpha over 2 to give you the negative z-score that correlates. But if this is my actual mean and it's not 0, I don't want the standardized value, I want the actual value. That's where the second part of the formula comes into play. It changes it back to the normal value rather than the standardized. I will tell you on Hawks, it's going to have you put in the positive z-score, not the negative. We know that because of symmetry, that this will be a negative 1.96, and over here it will be a positive 1.96. So easy way to fix that, you just go up here and put a negative in front. That'll switch the sign. Okay, so that's my positive z-score. So then, the next thing we need to do is just check out to make sure we have all of the information. So x bar was here. We got it. We just found this z alpha over 2. Population sigma, okay, that was given to us. N was given to us. We're ready to go. What I want you to do, though, for every single one of these is think back into the two pieces, the differs by. So we're starting in the middle, and we're adding and subtracting some margin of error, or that differs by amount. So just below, we're going to group two things, the x bar and the margin of error, and we'll calculate both of these. The first one was given to us. The second one we're using this formula for. So equals, it says grab the z-score first, and we're going to click on that. We found it. Times, then we want to do the standard deviation. Okay, that was up here, population sigma, divided by the square root of n. Now recall, this second thing is really the standard deviation of the sample mean. Okay, it's just doing this whole thing in one go for us. So now that we know those two values, we can find our low side and our high side of our interval that creates that 95% boundary. So on the low side, we're going to start with the mean and subtract the value. And then on the high side, we start with it and add the value. So my interval goes from 110.8 to 189.2. I'm saying that I can be 95% sure that the true mean is within this interval, meaning in 95% of all of the intervals created here, the true mean will actually show up. So we're going to interpret this as we are 95% confident that the true mean, and we'll add context if we have it. Now this was just a plain Jane equation, so we didn't ever know what this mean was referring to, but we would add context if we did. The true mean falls within 110.8. Again, we would add context if we had it, and 189.2. And that's a confidence interval. Okay. Now, there is an Excel function that can find the confidence for you without having to calculate the z. The reason why I don't usually teach it that way to start with is because this is alpha, not alpha over 2, and this standard deviation is the standard deviation that was given to you, not necessarily the standard deviation of the sample distribution, the sample means. So there's kind of misleading of which one we're working with. So you have to be extra careful on it. But then the size is just regular n. I will show you just to the side. You can get that same thing using it. It's equals confidence dot norm, because it's a normal curve. Alpha was my leftovers, the 0.05. And then standard deviation was at 200. And n was here. And it gives you that same value. Okay, you are welcome to use that. This is not on your note card. This one is. That's kind of something you have to consider as well. Alright, we already talked about this is not the probability that mu falls in it is 95. We're just saying of all of the confidence intervals from 20 random samples. Now ours wasn't 20, but this is kind of the visual for it. Then our true mean, say it was here, it's going to fall in 95% of those intervals, not all of them. Okay, that's what my 95% confidence is. So really, really clarifying here, you're writing we are 95% confident. That's not equal to that there's a probability of 95% or 0.95. Okay. All right, so this is what we just went over. Start at the middle, add the margin of error. Sometimes, though, if we're trying to, the whole goal of this, y'all, is we're trying to estimate the population parameter of the mean. But if we don't know the population parameter of the mean, then we probably also don't know the population parameter that is the standard deviation. Okay, so that's where the second one comes in to play. So if we don't know mu and we don't know sigma, then we're going to use a t-value instead of a z-value. It still is shaped kind of like a bell curve. It looks similar to a normal, but the difference between a normal distribution and a t-distribution is really going on in the tails. Okay, so the tails are thicker or higher than when we see the normal bell curve. Remember, we said almost all of the area under the curve is within 3 standard deviations of the mean for a normal curve. There's more room left for error for a t-distribution. That's really it. Now, it still measures standard deviations away from the mean. What's different is the arguments of the function. Okay, when we talk about t, there's a new argument or a new thing that you have to deal with, and it's called degrees of freedom. Degrees of freedom just tell you how many of the how many of the sample values can vary. So it's equal to whatever your sample size is minus 1. So if you have a sample size of 10, 9 of those values can vary. One of them has to be set. So that's all a degree of freedom is. It's just n minus 1. Okay, so with that, just like when we're finding the z-score, we're still going to have alpha over 2, but we have to set this second argument of the n minus 1, and it says n minus 1 on your formula sheet. We're just like with the z-score using a dot inverse. We just don't have to have that norm.s. S goes with z, t goes with t. So how a problem is going to look for something like this is when we list out our items, we won't have the population standard deviation given to us. So that's why we really have to be clear with our symbols and making sure we know whether this was a population parameter or a sample statistic. So this one, it says, the following is a random sample of annual salaries of high school counselors in the U.S., assuming that the distribution is approximately normal. So this time they told us that it was approximately normal because our n is very clearly not bigger than 30. We only have a few samples given to us here. Then it says, construct a 90% confidence interval for the mean salary of high school counselors across the U.S. and interpret. So first thing we were given was the confidence level of 0.90 or 0.9. And then we're given sample information, but that's it. In order to construct an interval, we need two things. The thing that goes in the middle, the sample statistic we're working with, today it's mean. Okay, so we need our sample mean. And you can just call it X bar. We're practicing with the symbols from the note card. And then we also need the margin of error. In order to calculate the margin of error, here's what you need to know. Were you given a sample standard deviation, or, like up above, were you given the population standard deviation? That's the entire difference. So here, we weren't given either. That's the thing. But we were only given sample data, and that lets us calculate the others. Okay, we're going to start with sample mean. We weren't given it because we were given those individual values in the sample. We can calculate it equals average using Excel. Okay, so we're going to do that here first for our X bar. Then, I'm going to go ahead and delete this margin of error for right now because we've got to find these other things, S and N, because we were only given sample information. Make a note of that. Only given a sample. And because of that, we're going to use equals standard deviation, but dot S, and do the same thing to calculate it. Now, when we're given only sample information, then we have to make sure that we are using a t distribution instead of z. And n, we can literally count here, 1, 2, 3, 4, 5, 6, 7 in my sample for it. Okay, putting this all together, we need this t using equals t dot inverse. It says the probability, and this is where I want you to practice with your formula sheet. These on Excel are not going to match what's on your note card intentionally. Okay, Excel says put this in and put this in. Your note card helps you remember what each of those represent. So the first thing, the probability, is your alpha over 2. And recall from last time, that corresponds to your confidence level. So get rid of that. My confidence level was 0.9. So then alpha over 2 would be the leftovers, 0.1 over 2, so 0.05. So now my t inverse, I can put in that alpha over 2, and then n minus 1 is 6. So there's my t-score. Remember, this is an interval around the mean. If it helps you to draw it out, you can. So this is a z of -1.9, and this is a t, positive 1.9, and Hawks is going to want the positive 1 for your math. Okay, for me, the thing I'm going to grade is the margin, or excuse me, the interval, which is calculated by the margin of error and the mean. So let's go to that. X bar and margin of error. X bar we already had up above. I'm just going to go grab it. I like to put them together so we know what values to use to construct our interval. And margin of error is this first, the t-score, grabbing it, times standard deviation of the sample, we calculated that one, over the square root of our sample size, n. Okay, now that we have that, we can find our low side of our interval and our high side rather than in the t-scores, but the actual numbers related to our mean. So starting with the middle and then subtracting the margin of error, and then starting from the middle and adding the margin of error. So we can say we are 90% confident that the true mean, and this time we do have context, so it's talking about the true mean of high school counselor salaries in the U.S. falls somewhere between my two values that I came up with, the 39,978 and the high value of the 55,922. Okay, and so the rest of these are just all mixed together. Okay, so we're going to be looking for all mean today, but the big difference is recognizing, is this a situation where I have the population standard deviation, or is this a situation where I don't have it and I can calculate or am given the sample information instead?